Okay, everyone, thank you for being here. Let's go ahead and get started. I'm Rob Jackson in Earth System Science, and it's a pleasure to be here today to be with Sam and go over his work. About 4 years ago, I was sitting in my office, minding my own business, trying to get something done, and there's a knock on my door. And it was Sam, of course. And usually when you get a knock on your door, it's often something to do, or and you're grumbling as you get up from your desk. But with Sam, it worked out wonderfully. I had never heard of this department called Applied Physics, so that was a new idea for me. And what a fantastic idea it is, I would say. And if there are any other applied physics students out there, he can also come knock on my door. So we got to talking. He, his record was exceptional. He'd gone to Queens like my dad, which is not the best reason necessarily, but I'm an easy guy. He also went to Oxford, did well in both places, mathematical physics and mathematical computation. Won awards all the way through. Had worked at CERN before he came to Stanford. And so we decided to work together. And not only was he a fantastic student, but he was also free because he won data science scholar fellowships, Goldman fellowships. So it's been a really marvelous relationship. And on top of that, he makes a mean pisco sour, which is also not a great reason to pick grad students, but it doesn't hurt. So it's my pleasure today to introduce Sam, and he'll tell us about his work for the next 50 minutes or so.
Thank you very much, Rob. Queens is a great reason to hire any grad students. Thank you all for being here, both in person and on Zoom. I'm excited to share with you all my work on methane mitigation for climate restoration. The motivation behind my PhD is that global warming is already wreaking havoc on humanity through heat waves, droughts, floods, and extreme weather events. It's also devastating for all other forms of life, acidifying the oceans, bleaching coral reefs, and putting numerous species on the verge of extinction. Most of these impacts are continuous. A marginal increase in warming causes another heat wave, another couple inches of sea level rise, another extinct species. But there are also certain warming thresholds beyond which climate tipping points might occur, like Antarctic sea ice collapse or the melting of glaciers. Once they happen, it's irreversible. We therefore need guardrails for global warming, both for the continuous impacts already devastating and for the tipping points with their unknown thresholds and unknown consequences. This is why the Paris Agreement exists. It's a legally binding commitment from almost every country on Earth to keep global warming well below 2 degrees and ideally below 1.5 degrees. Unfortunately, greenhouse gases are building up in the atmosphere, warming the planet like a blanket. It's already 1.1 degrees warmer than pre-industrial times, and we're on track for 2.6 degrees of warming, if current climate pledges are fulfilled. If they're not, we could fly past 3 or 4 degrees of warming. Moving from our current trajectory down towards a safer path that keeps warming below 2 degrees will take the simultaneous reduction of all greenhouse gases, particularly carbon dioxide. My PhD work is about how methane, understudied and undervalued relative to its importance, could contribute to keeping global warming below 2 degrees. Carbon dioxide is the main driver of global warming, contributing 0.8 degrees, with methane in second place contributing 0.5, and other greenhouse gases contributing 0.2. This 1.5 degrees of warming is partially offset by 0.4 degrees of cooling from other human-caused emissions, mainly sulfur dioxide. As we stop emitting those other cooling gases and aerosols, some of this warming will be unmasked. So the problem is actually worse than it first appears. Despite methane causing 1/3 of greenhouse gas warming, it receives only 1% of international climate finance. Interest in methane is growing, but it still isn't getting the attention it deserves. Methane and carbon dioxide are the two most important greenhouse gases, but they behave very differently in the atmosphere due to 3 crucial differences: potency, atmospheric lifetime, and atmospheric concentration. Methane's shape makes it a much more potent greenhouse gas than carbon dioxide, as measured by radiative forcing, the amount of power radiated through a given area. I'll use an analogy to describe radiative forcing. Imagine you have a patio heater up in the atmosphere, blasting hot air down at the Earth. That's what a ton of carbon dioxide contributes in terms of the watts per square meter. A ton of methane, on the other hand, is equivalent to 120 patio heaters at the moment of emission. However, carbon dioxide has an atmospheric lifetime of centuries, while methane only lasts for around 10 years. So while the relative potency is 120 times higher at the moment of emission, it decays rapidly over time. Finally, the background concentration of carbon dioxide is 420 parts per million, while for methane, it's only 1.9. We need to rapidly cut all greenhouse gas emissions to limit warming to 2 degrees. Unfortunately, the atmospheric methane concentration is rising rapidly, as shown in black here, and it's already 2.6 times its pre-industrial value. To stay on a trajectory that is consistent with limiting warming to 2 degrees, we need to reduce anthropogenic emissions from their current level of 380 million tons per year down to only 200 million tons per year. The demoralizing thing here is that lowering anthropogenic emissions to 200 million tons per year would take implementing every single known methane mitigation strategy simultaneously, no matter the cost. And it gets even worse. Global warming causes warmer wetlands, which are then more productive sources of methane, warming the planet in a feedback loop. The 2-degree consistent scenario I showed on the previous slide, and pretty much all scenarios used in climate science today, don't take this feedback loop into account. For a sense of scale, by 2050, the increase in wetland emissions is estimated to be the same size as current US methane emissions. So there's this enormous methane problem with anthropogenic emissions we don't know how to address and natural emissions rising out of our control. There are 3 main ways that this problem could be mitigated in rough order of difficulty. First, you can avoid emissions in the first place, like reducing demand for beef. Second, you can oxidize methane at its emission sources, such as flaring. And third, you could potentially oxidize atmospheric methane. Most of today's talk will be general and will apply to all 3 of these. And then the last section will just be about oxidation, and I'll explain it in more detail then. Today, I'm going to present 3 sections of work that I did during my PhD. The first 2 sections are all about how we should value methane mitigation. I'm going to describe the cooling impact that methane mitigation has, and how we should compare methane and carbon dioxide relative to one another. The third section is about where a specific type of methane mitigation, methane oxidizing reactors, could be applied. I'll start by talking about the cooling impact of methane mitigation. I'll make 2 simplifications for clarity. First, I'm going to use the word removal because we were thinking about atmospheric removal during this paper, but it generalizes to the other types of mitigation. And second, I'm only going to talk about the temperature impacts today, even though methane mitigation also has air quality and crop yield benefits. There had already been a lot of work done quantifying the temperature impacts of methane mitigation, but it all had 2 key limitations. First, the models used to calculate the impacts didn't include this wetlands feedback. Including the feedback ends up increasing the impacts of a marginal emission of methane by about 15%. Second, and more importantly, the old models had no way to modify emissions. Fortunately, I happened to get into this field as some pioneering model development work was being done over in the UK by Fiona O'Connor, Gerd Fulberth, and Chris Jones, who were kind enough to host me there and let me run some of the early simulations using their model. They developed the first Earth system model that could interactively model methane sources and sinks, including the wetlands feedback. The main benefit of using an emissions-driven model is that we can connect emissions, the thing we actually have control over, with climate change. The old models were concentration-driven, so you could connect concentration with climate change, but this new UK model extends it towards a more fundamental understanding of how emissions impact the climate. In this work, we ran a number of simulations, which I'll describe shortly. Then I'll present a general result we derived, and then a few example results. We wanted to see what this new model would tell us for scenarios on opposite ends of the optimism-pessimism spectrum about where we're headed in the future. We hypothesized that we'd find stronger impacts of methane mitigation in optimistic scenarios due to a nonlinearity between radiative forcing and methane concentration. There's a whole body of literature on future climate projections about where we're headed based on the challenges humanity will face in mitigating climate change and adapting to it. These are called the Shared Socioeconomic Pathways, or SSPs 1 through 5. Here's the whole scenario database with carbon dioxide concentration in 2050 on the x-axis and methane concentration in 2050 on the y-axis. We used 3 scenarios from this database. The first is SSP1, an optimistic scenario shown in orange in the bottom left. The second is SSP3, a pessimistic scenario shown in black in the top right. And the third is SSP3, low near-term climate forcers, which is the same as SSP3 in terms of carbon dioxide, but it shows what could be possible in terms of drastic reductions in near-term climate forcers like methane. We took the difference between this scenario and SSP3, the methane difference, as a hypothetical baseline methane removal scenario, and we called this low CH4. We wanted to get a generalizable result about the cooling impacts of methane oxidation, so we developed a set of simulations based on those baseline SSPs. In this first category of simulation, we varied the amount of methane removed. So time is on the x-axis, and the global methane removal rate is on the y-axis. Lower down or more negative means more removal. The black line is SSP3, the baseline, and then the gray line is that low CH4 scenario I just mentioned. We then extrapolated and interpolated between these to develop a set of simulations. So x0.5 means half the removal of the gray curve, x2 means double, and so on. In the second category of simulation, we varied the timing of methane removal. We kept the same amount removed between now and 2100, but varied when it started, either in 2020 or 2030 or 2040 or 2050. And as you can see, if you have to remove the same amount of methane by 2100 and you start later, you have to ramp up to a higher removal rate in the second half of the century. Before I can show our results, I need to define a key variable that we came up with for this work: the effective cumulative removal, which is the mass of methane removed that otherwise would have been in the atmosphere. It's the integral of the removal rate, R, multiplied by e to the negative time over tau, methane's atmospheric lifetime. Here's how I think about the effective cumulative removal. If I took a ton of methane out of the atmosphere today and looked at the atmosphere tomorrow, there'd be a ton less methane. But if I took a ton of methane out of the atmosphere today and looked at the atmosphere 1,000 years from now, most of that methane wouldn't have been in the atmosphere anyways due to its 10-year lifetime. So the cumulative piece here is just that we sum up or integrate the removals done at different times. And the effective piece here is that we scale them all by this exponential factor that takes into account when they occur. It turns out that if you plot the effective cumulative removal against the global mean surface temperature reduction, for all of these simulations, you get a near linear relationship. And the slight curvature you see is due to a time lag between radiative forcing and temperature. We defined the slope to be the methane climate response, the sensitivity in global mean surface temperature to the effective cumulative removal. For the pessimistic scenario shown here, the lines go down by 0.17 degrees for every petagram of methane effectively removed. So the MCR for the pessimistic scenario is 0.17, and for the optimistic scenario, it's 0.25. So as we hypothesized, you get more bang for your buck in an already optimistic scenario. The methane climate response we defined here is analogous to a whole body of literature already established for carbon dioxide, where they have the transient climate response to cumulative carbon emissions. The difference here is that for methane, you have to scale by this exponential factor to make it effective. I'll now share a couple specific examples of how our results can be used. First, the delay of passing warming thresholds in a pessimistic scenario. In this scenario, the black baseline SSP continues rising linearly. Its temperature continues rising linearly, blowing by the warming thresholds of 2, 3, and 4 degrees. Methane removal lowers the rate of warming, delaying the onset of reaching these warming thresholds and potentially giving us time for adaptation. I've shown in dotted lines here, for each scenario, the times at which they cross the 3-degree warming threshold. We plotted the effective cumulative removal against the time at which these scenarios cross warming thresholds. So each of these 2s indicates the amount of methane effectively removed and the time at which it crosses the 2-degree threshold. Using the 3-degree threshold as an example, you can see that if you don't remove any methane, the 3-degree threshold will be passed around 2060. But then as we move to the right and remove more methane, the 3-degree threshold is pushed later and later in time. These linear relationships show that per effective petagram of methane removed, you can delay the onset of warming thresholds by about 4 years. Another example is the shaving of peak temperatures in the optimistic scenario. In this scenario, the temperature actually peaks around 2.6 degrees. So methane removal here is more about lowering the peak temperature rather than delaying the onset of warming thresholds. Each of these other methane removal scenarios has their peak temperature shown in dotted lines. It turns out that the most explanatory variable for explaining the peak temperature is the removal rate that you ramp up to right at the time of the peak. If you plot the removal rate against the peak temperature, you find that the peak can be reduced by 2.6 degrees per petagram of methane removed per year. The main takeaways from this first section are that methane removal can generally reduce global surface temperature by 0.2 degrees per effective petagram of methane removed. In a pessimistic scenario, it can delay the onset of warming thresholds by about 4 years. And in an optimistic scenario, it can lower peak temperatures by 2.6 degrees per petagram of methane removed per year. Now I'm going to switch gears and talk about how we should value methane and carbon dioxide relative to one another. This section is all about calculating the emission metric, the exchange rate between greenhouse gases like methane and carbon dioxide. Exchange rates are needed for policymakers because they allow you to calculate carbon dioxide equivalents when aggregating all greenhouse gas emissions. I'm going to argue that emission metrics should be aligned with the temperature goals of the Paris Agreement. I'm going to argue that we can use time horizons, which I'll define shortly, as the link between these two. There are 2 parts to this section. I'll first describe the established relationships between time horizons and emission metrics. And then I'll describe our novel relationship between temperature goals and time horizons before tying the 2 together. As I mentioned earlier, the relative potency of methane and carbon dioxide decays over time, as shown in this figure here. Climate scientists call this relative potency the global warming potential, or GWP, a measure of the radiative forcing caused by a gas divided by the radiative forcing caused by the same mass of carbon dioxide. Consider a ton of methane and a ton of carbon dioxide released simultaneously. Right at the moment of emission, the methane causes 120 times more radiative forcing, but due to its atmospheric lifetime of 10 years, this effect decays over time. The fact that the GWP varies so much over time is why you've probably heard different people use different numbers for its importance. Bernie Sanders will tell you that methane is 84 times worse than carbon dioxide because he's using a 20-year time horizon. The EPA will tell you that methane is 28 times worse because they're using a 100-year time horizon. They're both right, but it all depends on how you value the far future against the near term. In the 1990s, the time horizons of 20, 100, and 500 years were given as representative examples, but stressed as not having any special significance. The Intergovernmental Panel on Climate Change, the IPCC, decided that we needed one standard time horizon, so they took the middle of these three options, 100 years, and nothing has changed since then. There are good arguments for standardizing with GWP 100. It's good to avoid different countries and companies cherry picking which emission metric they want to use based on their own goals. It's definitely beneficial to standardize. The issue I have is which value is used for that standardization. The 100-year time horizon is completely arbitrary, chosen exclusively out of convenience and the fact that we humans have 10 fingers, so we like nice round base 10 numbers. I wanted to create a framework to reduce the arbitrariness of this time horizon decision. To align time horizons with temperature goals, we first needed to figure out the times at which different temperature peaks would occur. To do this, we used the IPCC scenario database with 10 different integrated assessment models, which are the panel names here, and 213 scenarios whose temperatures are shown over time in gray lines. The temperature peak for each scenario is shown with an open circle, and this time of peak and height of peak is the raw data used in this chapter. The key result we found is that if you take all of those peak temperature data and plot the peak temperature against the timing of that peak temperature, a linear relationship emerges. We can now predict the time at which a given peak temperature would occur. Our work builds on a lot of established literature by quantifying this relationship. As Bernson et al. Put it, a relationship between the target temperature and target year has not been derived in the literature. We provided this first relationship. Our result tells us that 2-degree consistent scenarios will peak around 2080, while 1.5-degree consistent scenarios will peak around 2045. So today, in 2024, the time horizon that aligns with the 1.5-degree goal is 21 years, and the time horizon that aligns with the 2-degree goal is 55 years. So we've developed this novel relationship between temperature goals and time horizons. There are already the established relationships between time horizons and emission metrics like GWP. We can then combine these relationships to derive a novel relationship between temperature goals and emission metrics. Shown here, on the x-axis is the temperature goal, and on the y-axis is the GWP. Now, as you can see, for lower peak temperatures, lower temperature goals, the emission metric is higher. And that makes intuitive sense because lower peak temperatures will happen sooner, so their time horizon is shorter, meaning the GWP is higher. For the 1.5-degree goal, the GWP that aligns with it is 81, while for the 2-degree goal, the GWP that aligns with it is 45. I've shown how to go from the Paris Agreement temperature goals to the time horizons that align with them. But we can also use our results to go in the opposite direction and take the 100-year time horizon and see what temperature peak it implicitly aligns with. It turns out that the 100-year time horizon implicitly aligns with a 2.6-degree temperature peak. So the 100-year time horizon is actually nicely aligned with our current inadequate climate trajectory, but far too long compared to the time horizons that align with the Paris Agreement. The GWP 100 value of 28 massively undervalues methane compared to the GWP values that align with the Paris Agreement. I think that we should use time horizons that are explicitly aligned with the goals guiding all of climate policy. The 100-year time horizon is implicitly aligning with our current inadequate trajectory. The main takeaway here is that methane is 45 times worse than carbon dioxide at limiting global warming to 2 degrees and 81 times worse for 1.5 degrees. We shouldn't use the 100-year GWP value of 28 because it massively undervalues methane. Which emission metric to use is still a value judgment. GWP isn't the only option, but the results I've shown demonstrate how we can reduce the arbitrariness of one piece of this decision, the time horizon. The IPCC is notoriously hesitant to change anything, so this will likely be a slow burn, but I hope that these results can one day help us value methane in accordance with its actual importance. In sections 1 and 2, I quantified how great it would be if we could mitigate methane. In this final section, which I did with Max Kessler, I'm going to focus on the practical constraints imposed on one type of methane mitigation, methane oxidizing reactors. To understand where these reactors could be implemented, I'm going to tell you about where methane comes from and the concentrations it's emitted at, how nature oxidizes it in the atmosphere to give it a 10-year lifetime, and the constraints that these reactors will have to satisfy. I'll first show how much methane is emitted at a given concentration, and then I'll demonstrate how reactors have concentration-dependent thresholds imposed on them. Combining these, I'll demonstrate how our framework lets you assess which emission sources might be best addressed with which reactors. First, an overview of where methane comes from. Methane is basically synonymous with natural gas, which forms underground when organic matter decomposes under high pressures. The other main way that methane is formed is by tiny microbes that produce methane as a byproduct in natural systems like wetlands and freshwaters, in landfills, and in the stomachs of cows. Our first novel contribution was to quantify the mass of methane emitted globally at a given concentration. This is important because oxidation is much easier at higher concentrations. Max and I synthesized the data about the concentration of methane emitted from a wide range of sources, as close to the source as we could find data for. Natural gas, for example, is about 90% methane, while landfill surfaces emit methane around 100 parts per million. We then used measurement tower data to estimate the concentration of methane emitted near these distributed area sources, like wetlands, freshwaters, and rice paddies. It turns out that the concentration near these area sources is so diffuse that it's basically indistinguishable from the background concentration of 1.9 parts per million. We then combined all of this data together into this bar chart here, with methane concentration on the x-axis and the global methane emission rate on the y-axis. As you can see, there are large contributions from the very high concentration methane, mainly fossil fuel sectors, between 100 and 1,000 ppm, mainly from cows, and then this huge blue bar down at near atmospheric concentration being emitted by area sources. We can also look at the same data cumulatively, summing up the amount of methane emitted at or above a given concentration. Above 40,000 parts per million, the methane is flammable, so you can set it on fire. Below that flammable limit, there are very few technologies proposed or developed to address this medium concentration methane. This is the huge unaddressed problem that a number of researchers and startups are trying to solve. So we've identified this problem, this medium concentration methane, where there are no commercial technologies available to oxidize it. Before I can describe the potential solutions to this problem, I first need to explain how nature oxidizes methane to give it a lifetime of only 10 years. Because this is the inspiration for methane oxidizing reactors. Methane is very different from carbon dioxide in terms of its fate in the atmosphere. Carbon dioxide has the carbon cycle, where CO2 is taken from the atmosphere, taken up by plants in the ocean, and then sent back into the atmosphere in a cycle. Methane, on the other hand, is not captured and stored on the Earth. Rather, it undergoes a chemical reaction called oxidation, where it reacts with oxygen to form carbon dioxide and water. Methane oxidation is a great thing for the climate because it converts methane, a highly potent greenhouse gas, into carbon dioxide, a much less potent greenhouse gas. Because of the weights of different atoms, each ton of methane oxidized gives you 2.75 tons of carbon dioxide. So you can think about methane oxidation as being like going from 120 patio heaters to only 2.75. The oxidation equation shown here is a simplified version of a highly complicated process that gets kick-started by something reactive. For methane, the main culprit is the hydroxyl radical, a hydrogen bonded to an oxygen with an unpaired valence electron that makes it highly reactive. More than 90% of methane will meet its demise at the hands of a hydroxyl. A couple percent will be destroyed by chlorine radicals and by methane-eating microbes in soils. A growing community of researchers seek to enhance this natural methane oxidation process. Approaches to enhance methane oxidation look quite different from one another. The simplest version is a methane oxidizing reactor, essentially just a black box with an inflow airstream and an outflow airstream. And inside that black box, the methane is oxidized somehow. There are some other less developed approaches that aren't constrained by a box. You can paint surfaces with photoactive materials. You could enhance the methane-eating microbes in soils. And you could enhance the atmospheric radicals to oxidize methane the way nature already does. In this work, we just focused on methane oxidizing reactors. The main thing that any methane oxidizing reactor needs is large quantities of air blowing through it, likely using huge fans. There are 4 main proposals in the literature for what could actually go inside that black box and do the oxidation. You could use heat. You could shine UV light at photoactive materials. You could shine UV light at gas phase molecules like chlorine to split it into radicals. Or you could use methane-eating microbes. I'm just going to talk about the first 3 types today, heat-based and light-based, because we can develop constraints for them based on their thermodynamics and energy usage. To assess the viability of any methane oxidizing reactor, we first need a set of necessary constraints. Not sufficient, but necessary. If a reactor used 100 times the world's supply of platinum, it probably isn't a great idea. The 2 I'll explain in this talk are climate neutral and cost neutral. The second thing we need is a set of justified best case scenario assumptions. For example, the best case projections are met for 2030 in terms of energy cost and carbon intensity. There's a mechanism in place to incentivize methane oxidation, and developments occur in adjacent fields like heat exchanger efficiency and LED efficiency. Together, these necessary constraints and best case assumptions give us a viability assessment. We can estimate the minimum concentration that a reactor could be applied at, or the technological breakthroughs that would be necessary for a reactor to be viable at a given concentration. The first constraint we defined is climate neutral, when the cooling benefit of oxidized methane equals the warming from the carbon dioxide emitted from the energy generation. We don't want to cause warming when we're trying to cause cooling. We limit our focus to the energy consumption of the oxidation process itself, but note that if energy was used to blow air through the system, this constraint would be even more prohibitive. Our results from section 2 fit in here because we need some way to convert between methane and carbon dioxide. And in this work, we used the GWP that aligns with the 1.5 degree goal. Next, we define cost neutrality to be when the economic benefit of oxidized methane equals the cost incurred to do that oxidation. There are huge uncertainties in the economic valuation of different greenhouse gases. Currently, they don't take tipping points into account. But there is an established body of literature estimating how much we should value different greenhouse gases based on their temperature, air quality, and crop yield impacts. If you take into account the 1 ton of methane oxidized and the 2.75 tons of carbon dioxide produced, the current estimate for how much we should value a ton of methane oxidized is about $1,800. So any viable methane oxidizing reactor needs to spend less than $1,800 per ton of methane oxidized. Now let's turn our attention to heat-based reactors. Heat-based reactors oxidize the methane by heating up all the air and then using a heat exchanger to keep some of that energy within the system, so they're not just spewing out air at 1,000 degrees. One example is regenerative thermal oxidizers, which operate at 1,000 degrees. And a more recent example is based on zeolites, porous crystalline materials that require only a temperature of around 330 degrees. For any heat-based reactor, getting that air up to that high temperature will take energy, and that energy has an associated cost and carbon dioxide emissions associated with its generation. The best case assumptions we made for 2030, based on the projections of other groups, are that geothermal will end up being the cheapest energy source and the least carbon intensive. And we also assumed that an 80% effective heat exchanger was used. Now, before I show our results, just to build up some intuition, if you took a cubic meter of air and heated it up to 1,000 degrees, and in that air you oxidized 1 part per million of methane, your intuition might be that the carbon dioxide emissions associated with all that energy generation would outweigh the benefits of 1 part per million of methane. But if that air was 90% methane, then maybe the story is different. Maybe the cooling impact of oxidized methane outweighs the warming from the carbon dioxide emissions. So concentration is very important for determining whether something is climate beneficial or cost effective. Here are our results with reaction temperature on the x-axis and concentration of methane oxidized on the y-axis. So in the purple area in the bottom right, it's both cost ineffective and climate detrimental. Cost ineffective meaning you're spending more on the energy generation than you're getting an economic benefit in oxidized methane. And climate detrimental meaning you're causing net warming when you're trying to cool. Then above that climate neutral line in the gray area, it's still cost ineffective, but at least now it's climate beneficial. It causes net cooling. Above the cost neutral line in the green area is both cost effective and climate beneficial. Each of these points on the figure, like Z1 and T1, are state-of-the-art heat-based reactors shown in terms of the lowest temperature they've operated at and the lowest methane concentration they've been demonstrated to work at. So as you can see, a number of them up in the 1,000+ ppm range are operating in that green, cost-effective, climate beneficial regime. To be cost-effective at methane's atmospheric concentration of 1.9 parts per million, the maximum reaction temperature is only about 30 degrees. So heat-based reactors don't currently appear promising for atmospheric removal. Instead of looking at 2 ppm and seeing what reaction temperature is imposed, we can also look at the current reaction temperatures and see what concentration minimum is imposed on them. So taking a zeolite reactor, for example, operating at 330 degrees, our results suggest that the concentration minimum imposed to be in the green cost-effective regime is about 300 ppm. So these types of reactors might be promising at point sources with elevated concentration, like dairy barns or coal mines. Now let's turn our attention to light-based reactors. There are two main types: photocatalytic, which involves shining UV light on photoactive materials like zinc oxide or titania, and photolytic, which involves shining UV light on gas phase molecules to split them up into reactive radicals. Light-based reactors also require energy to generate that UV, typically with LEDs. Again, we make a number of best-case assumptions for 2030. Solar energy is the cheapest way to generate UV, wind energy is the least carbon intensive, and LEDs achieve the highly optimistic efficiency of 70%. The key metric for light-based reactors is the apparent quantum yield, or AQI, which is the percent of incident photons that actually go on to oxidize a methane. The other key variable for light-based reactors is the wavelength of light. Higher wavelength light means you get more photons for the same amount of energy. Here are our results for light-based reactors with the wavelength of light on the x-axis and the apparent quantum yield on the y-axis. And note that in this figure, concentration isn't an axis. It's just shown in square brackets with each state-of-the-art reactor. Again, the purple area is cost ineffective and climate detrimental. The gray area is cost ineffective and climate beneficial. And the green area is cost effective and climate beneficial. As you can see, there aren't yet any light-based reactors operating up in the green cost-effective regime. To be cost-effective, the AQI needs to be at least 7%. The current best for photocatalytic reactors at 10,000 ppm is about 1%, and at 2 ppm, it's only 0.04%. The best for photolytic reactors at 50 ppm is about 0.8%. To become cost-effective at methane's atmospheric concentration of 2 ppm, the AQI would need to be improved by 2 orders of magnitude. At more concentrated sources, the AQI would only need to be improved by about 1 order of magnitude. These constraints we outlined here are already guiding the development of these technologies towards one day hopefully becoming cost-effective. So I just showed how methane oxidizing reactors have concentration-dependent constraints imposed on them. In the first half of this section, I showed how much methane is emitted at or above a given concentration. We can now tie the two halves of this section together using concentration as the link between them. For example, a heat-based reactor operating at 330 degrees has a concentration minimum imposed on it of 300 ppm. We showed earlier that there's about 250 teragrams per year emitted at or above 300 ppm. We can then tie this back all the way to section 1, where we quantified the cooling impact of a given amount of methane mitigated. If you could oxidize all of the methane emitted above 300 ppm, you could cool the planet by 0.35 degrees. Now, most of the emissions emitted above 300 ppm are best addressed with avoidance, not methane oxidizing reactors. But our framework allows you to understand which sources might be applicable for which reactors, and to estimate the total impact that methane oxidizing reactors or other mitigation strategies could have if implemented at scale. To summarize, I first described 2 ways to think about the benefits of methane mitigation. In section 1, using a new emissions-driven model, I showed that you get 0.2 degrees of cooling per petagram of methane effectively removed. In section 2, I showed that methane is 45 times worse than carbon dioxide at limiting warming to 2 degrees. Then in section 3, I outlined the concentrations that methane is emitted at, how heat-based reactors are already promising for point sources, and how light-based reactors require fundamental breakthroughs to be promising at any concentration. In conclusion, Methane is worse than we give it credit for. Methane oxidizing reactors are one promising approach to address the enormous problem of point source emissions, but they require substantial technological breakthroughs. I hope that the results and frameworks developed in my PhD will help shape this field towards one day meaningfully contributing to keeping global warming below 2 degrees. And with that, I'd like to thank you all very much for your attention. I think, yeah, we'll do like 10 minutes of questions and then I'll give some acknowledgements. Sam.
I have just one quick question about this. At the beginning of the talk, you were talking about methane emissions. It's megatons.
Yeah.
And then when you got to the removal, it was in petagrams or teragrams.
Yeah.
And I think if the tons are metric, that corresponds to gigatons for petagrams.
Yeah.
And
Megatons for teragrams.
For
Teragrams.
teragrams.
Yeah.
And I'm a little bit confused because that kind of sounds like, in the case of the petagram removal, that that's like 1,000 times more than the megatons units that were used for emissions. And I want to make sure that I don't have the wrong idea that you're talking about removing 1,000 times more than 100.
You're completely right about the first part. So
Okay.
megaton equals teragram.
Yeah.
And this is often the bane of our existence, trying to go back and forth between these. Anthropogenic emissions are about 380 megatons, which is like 0.38 petagrams. And then natural emissions are about the same size as that. So you can think of a petagram as being basically annual emissions of anthropogenic and natural, but it's still absolutely enormous. And so all of these units are kind of used knowing that they'll be scaled down. It's like 0.2 degrees per petagram. We're not going to probably remove 1/5 of the Earth's methane, but that's the like scaling factor. Paul?
So, fantastic talk. I'm just curious, when you talk about cost, is there any assumption of any sort of price on methane? And either way, what's your outlook?
Yeah.
Efficient future.
Yeah, great question. Implicit in all of this, implicit in that cost neutral line, is that someone will pay you $1,800 to do that oxidation. So implicit in it is this rosy best case assumption that there is a market mechanism or some private company who will pay you $1,800 to do that. I think that we're generally trending in that direction and that there's going to be a cost on carbon dioxide, on methane, on nitrous oxide. It will take time and it looks like it'll be kind of piecemeal getting there. It'll be that the government might give you a certain dollar value for methane if you do a specific type of mitigation that they can verify really well. Like if you go to an abandoned coal mine and you plop a reactor on there and you can really measure it well. But yes, implicit in all of this is someone's paying you for it. Yeah.
So between all the different bodies of government or industry that could have a say in change, whether it be the IPCC or the EPA, whatever it is, what is the one policy or standard thing that you would like to see happen or change to be made to have the biggest change in the world based on what you know?
Back to Paul's question is have a price on methane. Once you have a price on methane, 10 times more people will start trying to make these reactors. 10 times more people will start trying to get credits for reducing beef demand or plugging natural gas. And I think, yeah, a market mechanism will unlock the most there.
You addressed especially solution that could be implemented on the surface of the earth. Are there any geoengineering techniques that people are talking about? That would be, how would you compare them with?
Yeah.
Oxidizing reactors?
Yeah. Yeah, I kind of glossed over that. One, when I referred to enhancing atmospheric radicals, that's a whole category of potential solution. Because the methane oxidizing reactors need big breakthroughs to be feasible for atmospheric removal, people are thinking about these open system interventions. So one idea there is that you could spray iron aerosols in the atmosphere, and that would catalytically create more chlorine radicals, because chlorine is up in the atmosphere from sea spray. And if you could convert it into radicals, then that would oxidize the methane. So there are a number of proposals that look a bit like geoengineering, depending on how you define it, but they don't have one feature of geoengineering, which is that the types of geoengineering often talked about, like solar radiation management, have this worry of termination shock. Like they're not addressing the root problem of greenhouse gases. But if you did methane oxidation geoengineering, you're addressing the root problem of these greenhouse gases building up. Haley?
Yeah, awesome. Thanks. So if I understood correctly, first two parts of your talk made the assumption that you were looking at like existing technologies but different policies. I was going to ask, like, my hope and probably everyone's hope is that some like breakthrough technology comes and does really well and like can do things much better. Did you simulate for that? And if you didn't, how could you incorporate that into simulations or models?
Yeah, the first two sections are general enough that any technology could come along and mitigate methane. I think the way that I laid it out with the three types, there's this like avoidance, which in my mind is we know how to do a lot of this stuff. Policy needs to incentivize it. And then there's this oxidized methane emissions, which we need technology breakthroughs for the technologies that we've thought of. And then there's this oxidized atmospheric methane. And I'm with you that it would be great if something came along and could oxidize atmospheric methane, like these iron aerosols. But the first two sections are general enough that a new technology could come along. Charlie.
I have a question about like the cost of the methane oxidizers. And so I was curious, like, does this cost just focus on the energy consumption, or does it also like sort of cost, labor, technology, like organization costs? And like if those aren't included, like how would that change the picture, like scale?
Yeah, great question. So we tried to paint as best case a picture as we could. So these are just the costs of the energy generation for oxidation. They don't include the energy for airflow. They don't include like capital expenditure, actual materials. They're a bare minimum. There are ways that you could potentially circumvent these constraints. Like if you could find waste heat from a geothermal plant, then you wouldn't have to pay as much for it and you wouldn't have as much carbon emissions associated with it. So there are ways to maybe circumvent it with clever approaches, but for the most part, it's a bare minimum that doesn't take into account all those things you mentioned. Lara.
So I was thinking about the time horizon and specifically the fact that previously the 100-year time horizon was completely alternate based on these considerations. And essentially what you've done is said, okay, but humans value this particular outcome over this particular horizon. That's resolved in a way that's going to allow us to do science in favor of that happening. And I was just wondering if you had any general thoughts about doing science in a way that embeds kind of the values and the things that we actually want to get towards, because you have this arbitrary metric that has been in place for many years, seems to have screwed up the ways that people think about this problem. How do you avoid that happening?
I'm going to have to do a philosophy of science PhD or ask you. One thing I'll say is that the Paris Agreement is already kind of arbitrary. and the 2-degree goal is a political goal rather than like fundamentally rooted in science. And so more of what I would argue is that we want to align all of our strategies rather than thinking that this 2-degree goal is somehow this objective truth that we need to get everything in line with. It's just that we should have our other climate policies, if they're targeted towards a goal, be in alignment with each other. I think I'll move to acknowledgements then. Oh, yeah. Doesn't look like. Yeah. Okay. I want to start by thanking my collaborators on all of this work. Fiona, Gerd, and Chris in section 1, Max in section 3, and then Rob Buchler and Max in this forthcoming work that I didn't get a chance to talk about. I also want to thank my funding sources, NSERC, the Woods Institute for the Environment, and the Stanford Data Science Scholars Program. Thank you to the whole team at Spark Climate Solutions for being wonderful collaborators and mentors in broadening the scope of how I view this field of methane removal. Thank you to my committee for being here. Harold, you've always been very helpful in helping me navigate being an applied physics student, figuring out Earth system science, so thank you for that. Chris, thanks for flying back just for this from Patagonia. Ben, thank you for agreeing to be on my committee, and Ed, thank you for chairing this committee. Much appreciated. Thanks to the whole Jackson Lab for being a great academic home at Stanford. It's always great to see the breadth of work you're all involved in. And finally, a huge thank you to my advisor, Rob Jackson, for taking a risk on a lost and confused physicist and introducing me to the world of climate science and methane removal. I'm inspired by your thoughtfulness when determining what research questions are worth addressing. But what makes you such a special advisor and mentor is the thoughtfulness you show to your grad students and postdocs, encouraging them to be multidimensional, thriving humans. So thank you. Oh boy. The first community that shaped my time at Stanford was the triathlon team. Far too many names to name, but thank you all for the early morning sufferfests, the goofiness, that one swim I attended, and the wonderful welcoming energy you all helped cultivate. Second, the community associates and RAINs, hosting events and building community among my fellow grad students. This overwhelmingly social experience was the perfect foil to work during the day that often just involved looking at my computer. I want to give special shout outs to a few CAs who taught me many things about community building and friendship. Joan, Irene, Charlie, and Pearl. The next group of people who shaped my time at Stanford are the inspiring friends who I get to adventure with. My relationships are deepened and enriched by being in nature, in the mountains, on bikes, often suffering and sharing food afterwards. So thank you to Thomas, Hannah, Blair, and Bean for being the people most willing to commit to a bit. Thanks to Nala, Catherine, and Celia for your infectious enthusiasm and stoke for anything from a redwood to a nice lake to a backcountry ski trip in Alaska. And thank you to Paxton, Margaret, and Brian for going on truly the adventure of a lifetime with me, bikepacking in Peru. And I'd like to particularly thank Deard for being my main support system and adventure partner throughout COVID. The last group of friends who made my time at Stanford so special are those who I got to live with and who made our apartment in Rains feel like a home. Big Sur, Terminator, Pan, Sausage, Potato, Kachoo, Llama. Thank you all for the endless love and laughs. You all taught me how to be a better, sillier, more loving version of myself. The past 5 years were the best 5 years of my life. Thank you so much for your friendships. I'm contractually obligated to thank my future sponsor, Kettle Chips, with honorary mentions to Miss Vicky's gluten-free pastries, and the dining halls. Finally, I want to thank my wonderful family for making this time at Stanford possible. I'd like to thank my grandparents, David and Susan, who are here in person today, for your support and generosity throughout my whole time here. My other grandma, Mary Alice, is with family in Ontario, watching this on Zoom, celebrating her 90th birthday today. So happy birthday, Grandma. And my other grandpa, John, passed away before he could see me defend, but I know his critique would have been absolutely scathing about how there wasn't enough chemistry at all. Minor shout out to my brother for keeping me humble. Finally, I am who I am because of my parents, Brad and Jocelyn. They're both so enthusiastically supportive of everything that brings me joy. They make me feel empowered to live life as if everything is rigged in my favor. Thank you so much, Mom and Dad, for your unwavering support and love throughout my life. And with that, thank you all for being here. And now you all have to leave. Yeah, I think we'll just stay here. That's why. All right, good luck. Appreciate it. Thank you. Thank you so much.
That was like the most understandable talk that I've ever been to, in like such a good way.
Yeah, yeah,
Like, it was awesome.